Well, I know you've got a lot of things you're doing this week and next week for this project exam that's coming up. But let's go right to the board. Let's talk about what's happening this week, and then we'll get into the new lecture material. Hoping students in the Tuesday, Thursday, 3:30 class help us out, fill out those minute papers. All right, what's doing this week? All right, homework number 3 due. End of the week, Friday, midnight. Just like prior homework assignments. Any answer that you need to use the computer to get, you need to include computer printouts, statistics printouts, along with your answers, and make sure you put that into a Word file and submit that to Canvas no later than midnight on Friday, November 10th for your 3rd homework assignment. Also this week, be looking for feedback via Canvas, okay, on that Canvas link where you turned in your bonus points printout. Be looking for feedback from your teaching assistants, okay? The TAs are obviously giving you the points, as well as checking your data and making sure that everything's the way it should be. And if there's any corrections you need to make, they're telling you. And so you can make those changes right there and then proceed on with getting your remaining printouts. So that's this week, okay? Early this week, make sure you take a look at Canvas for your project data feedback. And then, of course, throughout all of this week and next week, right up until the exam, at various times, the TAs will be moving from the Stat Lab into the CIS, one of the 2 CIS computer labs, either 1034 or 1035. In a second here, I'll show you the schedule, but it's posted on Canvas, okay, so you know you can always go there to get help, okay, from the TAs. And then I will do an exam review next lecture. So I'll go through all the printouts that you have to bring with you to the exam and relay that to the questions that I ask you on the sample exam in the class notes. So I'll definitely do a review next time for the exam. Now, that's leading right up to the exam. Let's move over to the smart board. First of all, here's a list of all the times that the TAs will be moving from the Stat Lab into one of the 2 CIS computer labs. So that's posted on Canvas, so take a look there. And on the times they're not in the CIS labs, they're back in the Stat Lab. So it's not like we're abandoning the Stat Lab. We're not. They're there. Remember, the Stat Lab opens at 9:30 in the morning on Monday through Thursday and ends at 8 p.m. Okay, that's that. Now, as far as the exam, number 3, well, that's next November 15th or 16th, next week, in class. Remember, you need to come to your regular scheduled classroom, class time. Of course, it's a 75-minute test like the first 2 tests. What's it going to cover? Chapter 12, which is the multiple regression chapter, and obviously specific to your project data. Really is specific to your project data. Just like in the previous exams, bring in your picture ID. You won't be permitted any calculators or cell phones turned on during the test. And like the second exam, you're going to be bringing in printouts with you. These are the 13 now printouts that you'll need to generate. They're clean again, which means no highlighting, no writing, no marking on them, other than your name, section. You can number them, of course. And one thing I need to point out to you, okay, please don't do this. I'm going to switch over to the overhead camera real quick here. Do not bring in this printout, okay? That is the one that you turned in for bonus points, the one that describes your data. That was to help us give you feedback, okay? We had to know what you were doing, what you were predicting, what your experimenting was, and so on, to see if everything made sense. But this should all be in your head. This is your knowledge. You bring this in with you, okay? This is the story that you're bringing in with you in your head. Don't bring this page in, okay? Don't bring that page in, the one that described all your variables. So please don't do that. It'll cost you some points. I don't want that to happen to you. Okay, so that's exam number 3. That's next week. But like I said, I'll be doing a review for that next lecture. All right, now let's do a review of last lecture. Last lecture, we got into residual analysis. And remember, residual by definition is an error of prediction, the difference between an actual Y and a predicted Y. And that helps us with checking assumptions on the random error terms. That's what we did. We spent the majority of that lecture on this material regarding residual analysis, testing the assumptions. Okay, that's what we're using it for. So one by one, let's just look at it. Remember, there's a graph that corresponds to each assumption for you to check. Okay, so there's a printout that you're going to be looking at for your project, for your data, that helps you check each assumption. So let's take a look at them one by one. All right, so first we start with the assumption. So let's start with assumption number 1. That's the mean error 0. Now, typically the problem will occur. That is, this will be violated when you have misspecified the model. That means the correct form of the model has not been proposed by you. Maybe you left out interaction or curvature or something like that. Maybe you left out an important variable. That's called a misspecified model. That's the problem. All right. How will the graph help us? Well, first of all, what is the graph? You're going to plot your residuals against your quantitative x. Using my example that I'm carrying through in class, I would plot my residuals against my years of experience because that's my x1. Okay, you're going to plot it against your x1, your quantitative x. That's printout number 10, by the way. That's printout number 10. And what are you going to be looking for? Well, a violation would be some indication of, say, curvature, like I'm showing here, okay, on this graph. Now, the remedy would be add the curvature back to the model. Obviously, it's not in the model because the graph shows some kind of a curvilinear trend. You would add it back to the model. And like I said to you last lecture when we went over this for the first time, this should not happen to you. You should not see this picture, okay? That shouldn't happen. That shouldn't happen because you should have tested for curvature. And if you did the test correctly, either you already have curvature in your model as it should be, and therefore you won't see this graph, or you have removed curvature from the model because it was not necessary and it shouldn't be in there in the model, and therefore you won't see the graph again because the graph wouldn't occur because there's no curvature to be added. So if you see a graph like this, you get down to number 10, you see a graph like this, you need to go back to your model building and make sure that you've done it correctly. You probably made some mistakes somewhere along the line. So anyway, that's the first assumption. All right, so you're going to check it just to make sure that that's satisfied. All right? The second one is that the variance of the error term is sigma squared constant. In other words, it's not going to change as you change the x's. That assumption is going to typically be violated when you have unequal variances. All right, so now how can we check for that? What's the graph? What's the appropriate methodology for checking for that? This time you plot your residuals against your predicted value of y. And that corresponds to printout number 11 on the list that you're bringing in with you. So printout number 11. What would the violation be? First of all, remember, and I should have stated this a little bit earlier, if you see a graph that has no pattern at all, that typically means no problem. So no pattern, no problem. You see a pattern, you see a trend, something like we're showing here, that's a problem. And that's a violation. As you can see, like this would be unequal variances. You have a tight spread on the residuals down low on the graph, and then a really big spread of the residuals as the y hat value, this is y hat, as that gets bigger and bigger. That's a violation, okay? Now, what would the remedy be? Well, the remedy would be to make what is called a variance stabilizing transformation, which is to model not y, but some transformation of y, like a square root of y or a log of y. Look, you're not going to do this. You're going to tell me about it, okay? If you have this violation, you'll tell me about it, what you would do in real life, but you're not actually going to carry this through. But this is how you would actually carry it through. You would actually change the dependent variable to some other transformed variable and then model it. Now, you don't have to tell me which transformation to use. Just say that you would have to, if this occurred, that you would have to make one, a variance stabilizing transformation on y. That's how you fix the problem, but you don't carry that out. All right, let's go to the third assumption. Third one is that the errors are normally distributed. Now, before we get into the details on it, remember, regression is very robust with respect to this assumption. The term robust, the word robust, means this, that even for slight up to moderate departures from normality, the technique still works well. Okay, so we're not going to be as worried about this assumption as we are about the other two and the fourth one. Okay, but still we need to be diligent and carry out the checks of this assumption because extreme skewness or lots and lots of outliers will cause problems. So that would be the problem, extreme skewness, lots of outliers. All right, now there's actually several graphs you'd look at here, several printouts you look at here. First of all, printout number 13 is a stem and leaf plot of the residuals. That just allows you to check for extreme skewness, okay? And I've drawn a line over there for the violation. If you saw something like this, that's extreme skewness versus some kind of a, nearly mound-shaped, bell-shaped curve, all right? Then you would have a potential problem. You also want to look at a list of your standardized residuals. Remember the z-scores that we had the computer calculate to determine whether or not our residual was an outlier? Well, it's the list of standardized residuals. That's printout number 9 on the list. And remember, you're looking for y outliers. That's any standardized residual in absolute value greater than 3. That's a y outlier. any standardized residual between 2 and 3, that's a suspect Y outlier. But we're looking for Y outliers, so that's anything greater than 3. Okay? So you take a look there and see if you can find any outliers, Y outliers that is. And then go back to printout number 10 and check it for something different this time. So you already have it checked earlier for another assumption. Now go back to printout number 10, that one where you plotted the residuals against the X1, number 10. And this time you're looking for an X outlier. And a picture I've drawn here illustrates it. It'd be a case where like all your data, almost all your data is down at one end of the scale, and then you got 1 point out here. All right, that'd be called an X outlier. So 1 point far away from all the others horizontally, not vertically, but horizontally. Okay, that's called an X outlier. So you're looking for those. And then in real life, the remedy is you investigate them. Don't just automatically eliminate the outliers, you investigate them. And maybe they're legitimate data points, then you keep them in the data set. But if they're not, then you would remove them. You, of course, don't have to do this. You just tell me what you would do. Oh, I have some outliers I should investigate to make sure they're legitimate data points. So that's checking this particular assumption of normality. And finally, the fourth one was that our errors are independent. And this is going to be violated when the errors are correlated. And that typically occurs when you have what is called time series data. Time series data. And we've defined this a couple of times in class. Way early on when we talked about a simple linear regression, we defined it. And then, of course, I defined it again for you last lecture. This is when your experimental unit is a unit of time, not a variable now. I'm not talking about the variable. So if you've got a variable measuring how long it takes you to do a task in minutes, that's not time series data. That's a variable that's measured in time. I'm talking about your experimental unit, like being a month or a year. And that example we did on the stock prices, actually the stock's rates of return, okay, was recorded over years. So year 1 was the first data point, year 2 was the second. So that's time series data. That's time series data. And if you have this kind of data, you're susceptible to violating this assumption. Errors being correlated. Okay, so you just need to tell me. There's actually no graph that I can give you here, because if you don't have any time, if you don't have time, the actual graph is to plot the residuals against time. But if you don't have time, you can't plot it, you can't graph it. So there's no graph you need to show me in your printouts. However, you need to tell me if you've got time series data, that is if your experimental unit is a unit of time. And if it is, then you are likely to be violating this assumption. So you just tell me about it, and then I might ask you, well, how would you fix the problem? And the way you fix it, and I didn't give you details on this, but the way you fix it is to actually, I don't know why I keep losing my pen. The way to fix it is to actually model the error term. So not only do you model the deterministic component, but you actually model the correlated error, recognize that it exists, and you've got to account for it. We'll talk actually more about that later in the semester. I think the last lecture I'll give, I'll show you how to actually do that. But right now, you just tell me about it, okay? So check to see if you have time series data. You should know it ahead of time. That's one of the reasons why we had you on your, for those of you that wanted early data approval to get the bonus points, we had you write down what your experimental unit was. So we could help you with whether or not you have time series data. So if you have an experimental unit of a month or a year, you've got time series data. And you're likely to be violating this assumption, okay? Well, that's the review from last lecture. Now, before we get into the new lecture, a couple of project notes. Okay? These, again, are coming from students that ask me questions via email, coming in to see me in my office, talking to the TAs when they see you down in the computer labs and so on. These are some typical things that come up. So a couple students had this question. They got real confused with the null hypothesis and the alternative hypothesis and the models. And I think one of the questions a student asked me was, well, which model is HO and which model is HA? Well, wait a minute. No, that's not how you should think. There's not an HO that corresponds to a model. What there is, remember, a null hypothesis has to do with beta coefficients. For example, the first test you conduct looks like this. And those two betas, beta 2 and beta 5, are betas associated with curvature terms. So see, you're testing a hypothesis about betas. And the alternative, for example, on this test is at least one of these betas is not 0. Now, how does that relate to models? Well, the result of the test, that is a reject HO or not, tells you which model is better. For example, on this test, this was the first one everybody did. This was the one where you compared model 1, that's the one that has the curvature, to model 2, and that's the one with no curvature. Both had interaction. But Model 1 does not. Model 1 does have curvature. Model 2 does not. We spent a lot of time on that, okay? So you conduct this test, and at the end of doing this test, then you're going to say to me, oh, Model 1 is better or Model 2 is better, right? If you don't need the curvature, that would mean HO is true, then you would support Model 2. If you do need the curvature, that would mean supporting H1. That would imply Model 1 is better. So that's how you have to think of these tests, okay? Don't think of HO as being a model. No, HO is a test for a series of betas to be equal to 0. And once you conclude, yes, they are equal to 0, no, they're not, then that leads you to the correct model. So that's one thing I want to point out. The other thing was, and this isn't going to happen to everybody, maybe only a few students, but you fit a model, one of the models we're asking you to fit, 1, 2, 3, or 4, and for some reason, you entered the terms right, but they got dropped from the printout. They don't show up in the printout. In fact, you even get a warning about it. And you're going, what the heck did I do wrong? Well, let me show you an example of what you could have done wrong. All right, I'm going to go to the computer screen here. All right, and remember our example on grandfather clocks. I know that's not the project data, but I want to use it. Okay, let's say I want to create a squared term, and I know some of you are doing that, obviously, for your data set, or you're going to do it. Some of you have already done it because you got the bonus points. Others are going to do it now. And you make a transformation. So I'm going to come down, I'm going to make a transformation. And here's what I'm going to do. I'm going to create an age squared variable. So I'm going to call it AGESQ equals, and for some reason I've just lost my mind. I just wasn't paying attention, whatever. And I'm going to type in equals age, not age star age. I made a mistake. Okay, but for some reason I just don't recognize it. Maybe I just lost my train of thought, got distracted, whatever. Didn't type in age star age. I just typed in age. So I've got a new variable called age squared, which I think is a square of age, and it's really not. It's really just age again. Anyway, I go ahead and do it. It adds that column. I don't bother checking that this column age squared is exactly the same as the first column age. It is, but I don't bother checking. I just see, oh, I got age squared and I'm good. And then I go down and try to fit a model that it has age squared in it. Let's do it. Okay, I'm going to go to statistics, linear models, linear regression, put my dependent variable, that's price. And let's say I've got a simple model that has only age and age squared in it. I'm putting those two terms in. I click OK. Oh, what happened? Some error message shows up that says age squared is too highly correlated with the other variables to be included in the model. It must be dropped from the model. But I don't know what to do because I don't know what that is. I'll just hit OK. And I get a printout. Oh, OK, I'm good. No, I'm not. Because first of all, the note shows up here on the printout again. And then look at the variables in my list, predictor variables. Do you see age squared anywhere in there? Nope. That can happen to you if you mess up on your transformations. Okay? So now we're trying to catch that. If you turned in your data early, the TAs and myself who were checking this, we're trying to catch that if you messed up. We might have missed it though. But if this happens to you, that's what happened. That's one of the reasons why that could happen. There's another reason. That means you don't have enough data points for each of the different levels of your qualitative variable. But this is the most common way it happens. So anyway, be aware of that. Be aware of that. Okay. Well, the new material for this class, which is the last bit of material that you're responsible for the exam, we're going to go to the PowerPoint for this class. This is lecture number, following on the class notes. Of course, it's titled lecture number 19, but because of the hurricane, we're really one off, so it's really lecture 18. And the PowerPoint, same thing. Whether your class notes are downloaded from Canvas or you got from ProCopy. Let's take a look. Okay? We're still in regression. Continuing on, so now, like I said, it's really lecture 18. We're going to finish up by talking about what I call problems or pitfalls. And there's two of them I want to mention. I've already mentioned several others up to this point, but these are two big ones, okay, that typically occur when researchers conduct a regression analysis. One is due to a phenomenon called multi-collinearity. It's a big word. A lot of syllables. Multi-collinearity, which I'm probably just going to abbreviate MC from now on. But I'll tell you what it is. This phenomenon occurs when your independent variables, that is your x's, are correlated. Now, you might think, well, isn't that a good thing? Don't I want my variables to be correlated? Well, you want your y to be correlated with an x. Yes, no doubt about that. But it turns out you're not going to want your x's to be correlated. That's an x correlated with another x. So we're going to talk about that issue. And then a second problem we're going to talk about, this revolves around a certain technique that's very popular. It's called stepwise regression. Okay, stepwise regression. It's not that that technique is bad. It's just that it's often very much misused. Okay, and so we're going to talk about this method and how it should be used, and then we'll also talk about how it's typically used incorrectly. And I want to make sure that you're aware of that. This is actually what is called a variable screening method. So we're going to talk about these two ideas, multicollinearity and stepwise regression. Okay? Let's start with the multicollinearity. There's a nice example in your textbook. It's in section 12.12, and it's on this idea of your x's being correlated. Like I said, I'm just going to abbreviate it MC for short. Here's the example. Real life study, Federal Trade Commission. All right, studies the different carcinogens that can occur when you smoke cigarettes. Okay, and they often do studies where they'll use cigarette smoking machines. They don't have people smoking the cigarettes, but they get smoking machines that smoke cigarettes, and then they gather the residue from the smoke and are able to measure a bunch of different variables that could lead to cancer and that kind of thing. Well, one of the variables is carbon monoxide content of a cigarette. It's bad for you, obviously, but it's a very hard thing to measure from these smoking machines. And what the Federal Trade Commission researchers have found out is that if they treat carbon monoxide content Y as a dependent variable, they have found out that it is very highly related to three other variables that are also carcinogens, but they're much easier to measure. For example, the tar content of a cigarette. It's measured in milligrams. It's easy to measure once they have the smoking machine smoke the cigarettes. Same thing with nicotine content. Measured also in milligrams, easy to measure. They call that X2. And certainly the weight of the cigarette's pretty easy to measure in grams. Those three things are very easy to measure. It's hard to measure carbon monoxide content. But they go through this study where they do get measures of carbon monoxide content and then try to relate it back to these other X's, figuring that in the future, if they really want to know the carbon monoxide content of a cigarette, they can predict it pretty accurately because they can measure these other three variables very easily. That's the whole idea. Now here's what the FTC knows about this data. They know that carbon monoxide content is positively related to all three of those variables. The more tar in the cigarette, the higher the CO content. The more nicotine, the higher the CO content. The more it weighs, the more the cigarette weighs, the higher the CO content. So it knows all that. FTC knows this. So anyway, they go ahead and they know that positive relationships exist, okay? And they go ahead and fit just a basic model. You know, we call it a first order model. Be something that we'd have presented to you, a few weeks back to you. So they get a model that has the three X's in it. You can see it's listed for you there with the dependent variable. And they get a printout. And I'm going to show you this printout. It's in the book, but I've got it here. And I put it in statistics form so you'd be familiar with the numbers on there and where to find them. So on the left-hand side, let's look over here first. Here's the regression of CO, which is the carbon monoxide content. Look at the list of variables. It's got tar in there, nicotine in there, weight. So those are our X's. Well, good there. And let's start looking at the model statistics that we typically use to evaluate the goodness of a model. Hopefully you know these, right? Where would you look first on a printout like this to evaluate the overall adequacy of the model? Where would you look first? What's a good place to look? Down here. Global F, right? You always want to look at the global F test first. It's significant. So that's telling us now, it doesn't necessarily tell us that the model is good or great. We don't know that yet. It's better than nothing, though. It's better than no model at all. It's called statistically useful. Okay, so it's got a statistically useful model. And then we probably pop up to the R-squared values, like the adjusted R-squared, for example, and it's over 90%. So over 90% of the sample variation in carbon monoxide content can be explained by these three variables. That's pretty good. Hard to argue against that number. Standard deviation is actually pretty small, 1.44. CO content is measured in milligrams, so that's being able to predict the carbon monoxide content within double that, about, what's that, about 2.8 or almost 3 milligrams, which is pretty small. So it looks like it'll give us a small error prediction. So things are looking pretty good as far as using this model, except the FTC is confused. Remember I told you they know that these variables are all positively related to CO. And they start looking at the beta coefficients. And they see a positive coefficient on tar. Well, they expect that, so that's good. But then they see what? A negative beta coefficient on nicotine and a negative beta coefficient on weight? Wait a minute, that doesn't make any sense. We know that nicotine is positively related to CO. We also know that weight is positively related to CO. But this printout's coming back and tell us we have negative related. I'm confused, really confused on this. And not only that, look at the p-values. Okay? The p-value for nicotine is not significant. The p-value for weight is not significant. Well, yet we know these variables are good predictors. The FTC knows this. What the heck is happening here? Confusion. Well, the confusion arises because of this multicollinearity issue. Let's look at this printout over to the right. This is just a printout, something like you're getting. Okay, I think it's printout number 2 if I'm not mistaken. Or maybe it's printout 3. I think it's printout number 3. Where you get a correlation matrix? Yeah, printout 3. And now these are the correlations between pairs of X's. So for example, here's a correlation. Look at this column, nicotine, and look at this row, weight. So this 0.5, that's the correlation between nicotine and weight. Those are two X's. That's a moderate correlation. That's not a low correlation, that's moderate. But a bigger problem exists when you look at the correlation between nicotine, column, and not CO, but nicotine and, oh, that printout's not the one I want. That's a typo. Okay, sorry about that. This CO shouldn't be CO. This CO should be TAR. So make a note of that, okay, in your class notes if you have that there. Cross off the CO in the row and CO in the column and call it TAR. It should be TAR. It's my bad. It's a typo. Sorry about that. So you're looking at the correlation between X, nicotine, and TAR. And so let's assume it's like that. And it's really high. It's 0.9 something. That's a very high correlation. That's a strong correlation between the two X's. The X's are correlated. That's a problem. That's what's causing the problem. Okay? The printout showing the negative betas, which don't make any sense. The non-significant t-test for a couple of the variables doesn't make any sense to the FTC. So the FTC should not doubt itself. It's not wrong about what it thinks about how the variables are related. What's happening is that two of the X's are really strongly correlated. That is, TAR and nicotine are very, very highly correlated with each other. And if I had the right correlation matrix, you'd see that. So like I said, you had to make that correction. Sorry about that. And that's what's called multicollinearity. X's highly correlated. And the reason why this is happening, it's all mathematical, okay? And I'm not going to go into the details on it. I'll just tell you that the reason why this happens is because when multicollinearity exists, the standard errors of the betas, the things they use to get confidence intervals and test hypotheses on betas, okay, those become inflated, too big. And if those become inflated, then the t-test value becomes too small, leading to non-significant results when they really should be significant. And that also leads to erroneous beta coefficients, betas that have the opposite sign. So it's this multicollinearity issue that's really, really important for us to check on prior to doing any regression analysis. Now, I know I didn't have you do this prior to doing your regression. I'm having you do it at the same time, okay? But you're going to look for this high correlation between your two X's, X1 and X2. You're not going to change anything if you find it, okay? But you're going to tell me, hey, I've got this problem. I've got multicollinearity. That could lead to problems in terms of my beta coefficients, my estimates, in terms of my tests. I could get confusing results. In real life, you'd check this ahead of time and you would nip it in the bud. You wouldn't have put the both variables in there. Like I say, it can lead to these erroneous results. So, how can we detect it? Well, I kind of mentioned it already. You're going to look at the matrix, the correlation matrix. You're going to look for high correlations between your X's. So you go look at printout number 3, okay? Pretty sure that's the one I want you to look at. Yeah, printout number 3. Let me get my list here. Yeah, printout number 3 is your correlation matrix. I'm going to show you that here in a second, okay, on my data when we go through all the printouts again. But you're going to go to your printout number 3. You're going to look for a high correlation between your two X's. I'm not talking about the correlation between Y and X. That's good. You want that on there. I'm talking about the correlation between your two X's. Like, for example, in my problem, my example I'm carrying through in class, it's years of experience is my first X and gender is my second X. That's what you look for. Look for a high correlation there. Now, other ways you could check for it, detect it, is if your global F test is significant and all the t-tests are non-significant. Think about that. That really doesn't make sense, does it? All the t-tests being non-significant would seem to indicate that none of the variables are important Yet the global f-test being significant indicates that at least one of the variables is important, so there's confusion there. That can happen with this multicollinearity problem. And then of course the betas with the opposite signs from theory. Okay? So it's easy for you to check it though. You're going to go right to that printout number 3 and check for see if you have a high correlation between your two x's. All right. Now what are some remedial measures? In other words, what happens if you do detect it? If you detect a high degree of correlation. Now I'm not talking about a moderate or low. Okay? I'm talking about like a high correlation coefficient between the two, like a 0.8 or a 0.9, something like that. Even maybe as high as 0.7, but typically 0.8 or 0.9, something like that. All right. If you see that, here's how you would fix the problem in real life. One way is an easy way. Just don't use both x's for the prediction equation. Don't use both the x's. For example, in the tar and nicotine example, what the FTC would do, it recognizes that both tar and nicotine are related to carbon monoxide content, but because they're so highly correlated with each other, they're essentially the same variable, they just put one of them in the model. Just tar, or maybe just nicotine, not both. That way they won't get confused. And then another way is you go ahead and put them both in the model, but you avoid inferences on the betas. In other words, you try to avoid the confusion. That's not easy to do. You have to be really disciplined to do that. It's like trying to avoid penalties and offsides in a football game, which apparently our football team here in Tampa is not too good at. Okay? You have to be really disciplined to avoid this, but it is another way you could solve the problem. So keep the x's in the model, just don't make any inferences about the betas. But number 1 is usually the typical way. Now you're not going to do this. You're not going to drop 1x if you have a multicollinearity problem. You're simply going to tell me what you would do, okay, if you had two highly correlated x's. Okay? But that's a really, really important issue to deal with anytime you look at a regression problem. It's something that all researchers need to be aware of, okay, this multicollinearity problem. Okay, now let's go to the second issue, okay? And it has to do with what is called variable screening methods. Let me give you an example, okay? In your textbook, I'm going to show you this on the overhead here in a second. In your textbook, there's a real-life study where a company had a lot of executives, very big firm, an international firm, had a lot of executives. And the board of directors wanted to build a regression model for the salary that they pay these executives. So the dependent variable was salary. And they had a lot of potential variables that they thought could be good predictors of salary. I'm going to show you the list right now. Okay? It's in your textbook. It's on page 753. Let me switch over to that. Get out of here real briefly. Go to the overhead camera. And I'm going to show you the list here. Okay? It's on page 753. There's 10 variables that they thought would be good predictors. Let me zoom in on those. Some are quantitative, some are qualitative. Let's practice a little bit. You tell me what's your quant, what's your quan. First one, years of experience. What kind of variable? Quantitative. Second one, years of education. Quantitative. Third one, board eligibility. 1 if yes, 0 if no. Oh, that's qualitative, obviously. Fourth one, number of employees supervised. Quant. Fifth one, corporate assets measured in millions of dollars. Quant. Next one, board member, yes or no? Qual. Age and years, quantitative. Company profits, quantitative. Has international responsibility, another qual. And then finally, company's total sales in the past month. So there were, I think if you count up, there's 7 quantitative variables and there's 3 qualitative variables. Okay, so that was their problem. That's what they wanted to do. All right, now let's go back to the PowerPoints here. Let's suppose, like you're doing, remember how your first model is a complete second order model. You have curvature in your model, you have interaction, right? Now you only have 2 x's. I limited you to 1 quantitative x and 1 qualitative x. But imagine if I didn't limit you to anything and I said to you, hey, get as many variables as you want. And you came up with this idea. Sounds like a good one. Let's use these 7 quantitative variables and 3 qualitative variables to model salary. Sounds pretty good. And let's start with a complete second order model. So we're going to put curvature in, we're going to put interaction in. Now if you do this, here's what happens. Remember how I showed you how you could write a model in stages to kind of keep track and really do a good job of keeping track of all the terms, making sure you don't miss any terms? And if you remember what I told you, I said the first stage only involves quantitative terms. So only deal with the quantitative. Well, if you actually count up how many terms would be in here, you would get 35. Here's where it comes from. The 7 here stands for 7 first order terms. 7 because there's 7 quantitative variables. The second 7 stands for 7 squared terms because there's 7 quantitative variables. The 21 stands for or represents 21 interaction terms. If you count them up, you actually get 21. x1, x2, x1, x3, x1, x4, and so on. You actually get 21. Add those up, you get 35 terms. And that's just the start. All right, now let's go to the second stage. The second stage, if you remember when I showed you how to write a model, involves only the qualitative variables. We know there's 3. So the first 3 has to do with the 3 main effects. First, for just the terms, 3 terms in there. Now, we're not going to square these terms, but we're going to interact them. See, squaring them wouldn't make any sense. We're going to interact them, though, because that's still just qualitative variables. So the 3 here stands for 3 interaction terms. Let's just say they're x1, x2, and x3. They're not. They're 3 other variables. Let's say it's x1, x2, and x3. Well, x1 by x2, x1 by x3, and x2 by x3. And what's the 1 stand for? That's a 3-way interaction. You could actually multiply all 3 together. And that's still an interaction term. And that's 7. So that's 7 terms there. Then you finish up with stage 3. And remember what I said here? This is actually the easy part that somebody, if it was skilled enough, could train monkeys to do this. Okay? You take all the terms from stage 1 and you interact them with all the terms from stage 2. And how many is that? Well, you just multiply the 2 out. 35 times 7 gives you 245. That's how many terms you would have in this model. Add them up and you get 287. That's one big model. But here's a problem. Not only is it tough to keep track of them, the sample size that this company used was only 100, sample size of 100. They had 100 executives they took a sample of. There's no way you can fit this model. It's impossible. Your sample size isn't big enough. You have to have at least a sample size as large as the number of betas in your model. So they can't even fit the model. Unable to estimate the betas in the model. So there's got to be some other technique that they can use here to help them fit a model like this. Well, the technique is going to be, let's not start with so many variables. All right, there's too many to start with. There's 7 quants, 3 quals, too many to start with. Let's not start with so many. Let's start with a fewer number. Well, how are we going to do that? Well, let's try to sift out or screen out the more important predictors from the least important predictors. So we're not saying that none of these variables are important. We're not saying that. We're saying that some are going to be more important than others. That's all. We're going to kind of rank them. Some are going to be more important than others. And let's sift through and find the most important predictors and separate those from the least important. Okay? And that's called a variable screening method. So we want to reduce the number of independent variables in model building, select the most important x's, eliminate the least important x's. Not that we don't think these are important x's, but we just can't afford to keep them in the model. We've got to cut down on the number of variables. So the popular method is called stepwise regression for doing this. Okay? And the terminology stepwise in front of regression makes actually sense when you see how it works. It's really done in steps. And it's all done via the computer. You're not actually going to have to do any of this yourself. You're going to point and click and do it. All right? So I'll show you how. Here's the steps that actually are conducted. Okay? And let's use our example here on executive salaries. Okay, remember we have these 10 X's. First, you fit all possible 1 variable models. You fit a model that has just 1 X in it. But you take turns on which X it is. First, you try X1, get some results. Then you remove X1 and put X2 in instead of it. Get some results. Then you remove that and put X3 in, and so on. And you do it for all 10 of the X's. And what the computer does is that now. And the computer picks out the X that has the largest t-value. In other words, the computer conducts a t-test on each of the X's. That beta multiplied by each X. Computer conducts the t-test. And one of these X's will be best because it will have the biggest t-value. So let's just say it's X1, that's what gets selected. Now how do you do the second step? Now the computer will fit all possible 2 variable models, and look what happens. It puts the variable selected from the first step in as one of the 2 variables, and then it alternates the second variable as many choices as possible. First it tries, we already put X1 in, so first it'll try X2, then it'll remove it and try X3, and then remove it and try X4, and so on until it tries all the remaining X's. And once again, it'll conduct a t-test on that beta, and the X that has the biggest t-value gets selected. Let's just say for the sake of argument it's X2. I think you see the pattern. Now you go to step 3. Now you're fitting all possible 3 variable models. And look, the first 2 x's came in from the first 2 steps. We alternate the third x as many times as possible, and then we pick the one that is best based on the largest t. Anyway, it keeps going in this pattern. Okay, step 4, so on. It's going to finally stop when the t-test on that beta coefficient that you're looking to select which x should be considered best, when that is no longer significant. So if it can't find significant t-values, it stops. So at some point it's going to stop. It won't add all the x's. It'll stop somewhere between 1 and 10. Okay? So it continues until no more significant x's. And here's what at first glance looks like no problem at all, looks like a great thing. The results are going to look really good. But it's going to be an issue. There's going to be a caveat. Okay? Before I tell you the caveat, I want to show you how easy it is to do a stepwise regression. It's really easy. Okay? I'm going to go to the computer screen again, and I'm going to get a different, the executive salary data set. So let me go get a different data set. I think I called it exec sal somewhere here. Let's find it. Yeah, exec sal right here. All right, there's my data. My Y is actually not in thousands of dollars. Y is actually log of salary. And you say, well, log of salary, Dr. Sinchak, I remember you saying something about log. Yeah, remember the variance stabilizing transformation we talked about? This company actually had to do that. They had to make a variance stabilizing transformation on Y. So instead of modeling salary, they're modeling log of salary. That's why the numbers look so funny. Okay? But here's all our 10 x's. X1, years of experience. X2, years of education, so on. X3 was a dummy variable. It's a 1 or a 0, and so on. There's the 10 x's. Okay, so that's the data. There's 100 data points there. Okay? Now, I'm going to run a stepwise regression using the software. Easy to do. Go to the statistics button, come down to linear models. Don't pick one of the ones we picked before. Not linear regression, not best subset regressions, but the one underneath it, stepwise linear regression. Stepwise linear regression. Pick that. So you click that. You got a lot of boxes to fill in, but it's really just 2 boxes to fill in. It looks like a lot of boxes, but it's really only 2. Dependent variables, easiest, start there. Okay, Y goes at the top. Then go down to the bottom and fill in, put all the other x's at the bottom. So x1 through x10 are going to go into the non-forced box, meaning we're going to try them all. We're not going to force anything in, we're going to try them all. Okay? You do that, you click OK. Results, boom. There they are. All those steps that I told you about, done in a split second. Okay? And look at these results. They're beautiful. I think I might have a, let me go back to the PowerPoints. I think I show this on the PowerPoints. It's a little bit easier to see. There we go. Yeah, they really look nice. Here's the x's selected, x1, x2, x3, x4, and x5. Here's the ones that were not selected, x6, 7, 8, 9, 10. The x's that are selected, look at the p-values for testing the t-tests on all those. 0.000 something, all significant. Look at the r squared and r squared adjusted, really, really high. Standard deviation, really, really small. And it wasn't very hard to get these results, was it? I did what, 2, 3 points or clicks? Boom, I had my answer. And I've got a beautiful model. And you're probably wondering why I am torturing you now on your project. You know, oh, I've got to go through these steps of a testing curvature, testing interaction. I'm all confused. HOHA, printouts, p-values, I'm all mixed up. Why do I have to go through all that? Couldn't I just done this? It's so much easier. Well, let me do this, please. There's got to be a reason why I'm not letting you do this. Okay, there's a problem with it. There's a problem. Let's see if we can figure it out. Okay? Go back to the steps. And think about all the tests you're doing. How many tests are being conducted in step 1 for this problem? There were 10 X's. 10 tests. Keep track. How many in step 2? 9 more. How many in step 3? 8 more, and so on. Remember, it went through, I think 5 X's got added. 10 plus 9 plus 8 plus 7 plus 6. That's way too many tests. The chance of you making at least one type 1 error is practically 1. way too many t-tests being conducted to stop after running a stepwise. Okay? So that's number one problem. Here's the second problem. Look at these models. Do you see any curvature? We're not even trying it. See any interaction terms? Not even trying. Now, that doesn't say that there's going to be curvature or going to be interaction, but there's no attempt even to see if there's any higher order terms, curvature, interaction. So that's the second major flaw. So I've written these down for you, so let's go to screen. So here's the problems with the stepwise regression. These large number of t-tests being performed inflates that probability of at least one type 1 error. And there aren't any higher order terms at all in this model. And there very well could be. We saw how dramatic that can change the prediction equation. You know, remember the grandfather clock collector? On how an interaction term, you know, made a big difference? Might not have tried it, though, if he ran stepwise regression. This is one reason, these two reasons why I don't have you doing a stepwise regression, okay, for your model building. Now, what's my recommendation, and what's anybody's, should be the recommendation for using stepwise? Use it only as a variable screening procedure. Notice that does not say model building. Variable screening. In other words, if you have too many X's to start model building with, like happened in this case, and you're forced to pick out the most important from the least important, this is a good technique to use. But you don't stop here. You now start model building with the smaller subset of X's. Now use those X's selected by stepwise regression and begin your model building like you're doing, considering curvature, considering interaction, comparing models. So see, this is just the beginning. So those that use stepwise regression and those that misuse it, start with it and end with it. No, if you have to use it, you start with it, but you don't end with it. It's just the beginning. You now begin model building to take care of these higher order terms and so on. So that's the recommendation for stepwise regression. That's why I'm not having you do it. There's no need for you to do it. You only have 2 X's. You don't need a variable screening method. You only have 2 X's. Now, if I allowed you to have 10, that'd be different. Okay, and if we had more time, maybe I would do that. I'd say go find 10 X's, run a stepwise regression to find your 2 best, and then model build with your 2 best, something like that. Okay? Now, in summary, you know, way back when we started simple linear regression, there were 5 steps to follow. Now, at the end of our discussion of multiple regression, the steps are much more complex. So let's kind of go through them. Okay, the steps that you would follow in a complete regression analysis. Step 1, select the important X's. Maybe it's like you did, just 2. Maybe you have a long list. And if you have a long list of potential X's, this is where you run the stepwise regression. Here's where it comes in, right away. Boom. But you don't stop here. So now you get down to a small number of X's. Start hypothesizing models, not just one model, not one, several, like you're doing for your project. Curvature, interaction, no curvature, interaction, that kind of thing. Now, don't do too many models because still you have to compare them and do tests to compare them, so you still don't want to do too many tests, but you hypothesize a series of models, one of which may be your best model. Go get the data, fit the models to the data using the software. That's step 3. That's what you're doing. Step 4, do your model testing. You're doing that. You're finding your best model. Maybe it has curvature. Maybe it has interaction. Maybe it doesn't have either. Global F-test, partial F-test, all the things you do to evaluate a model through model testing. Anyway, your best model shows up now. You should control your alpha that you test at. One easy way to do that is divide the alpha of interest to you by the number of tests you're going to do. Like, say I knew I was going to do 5 tests, and I want alpha to be 0.05, then I conduct each one at 0.01. All right, so then the step 5, hey, don't forget about residual analysis. Check your assumptions. Check your assumptions. You've got your best model now, but better check your assumptions. You're doing that. Now, I'm just asking you if you have to make any model modifications. In real life, you would make them. If you find violations of some of the assumptions, you would make your model modifications. And then that would possibly change your model. And then finally, you would finish up with making inferences on your best model. Making inferences on your best model. Confidence intervals for the mean of y, or prediction intervals for y, interpreting the beta estimates, maybe confidence intervals around those two, standard deviation interpretation, R-squared, you know, all the things you normally interpret for evaluating a model, you do. But those are the real steps involved with a regression analysis, okay? And I would tell you, it's, you know, if you guys can remember this, you're going to be in great shape out in the real world, because there's a lot of people using regression that violate, that fall into the traps, you know, encounter the pitfalls and aren't sure how to address them, that you'll be able to do by understanding this. Okay, now let me finish this class by doing this. Okay, you've got 13 printouts that, that you're bringing in with you to the exam. I showed you several times on how to generate all these printouts, so I'm not going to show you that again. You can go back and look at the lectures on that. Okay, but what I am going to show you are the printouts, and let's talk about what's important about each one. Okay, and then this will kind of lead into what our next lecture is, which is the review, exam review, where I go do the answers and the sample test. Let's talk about each one. So, you know, maybe you have your printouts with you. You can be following right along with me, okay? But at least be looking at the printouts that I've helped posted up on Canvas, sample printouts, you know, for your third exam. So at least you know what we're discussing. All right. So print number 1 is data listing, okay? You know, here for one reason why I had you do this for the bonus points was so we could check to make sure you created your squared terms correctly and your interaction terms correctly. Same thing you should be looking at it for. But probably the main reason you're looking at this is to make sure you know the range of your x values for prediction purposes. Because, you know, one of the printouts you're going to have to get is prediction intervals and confidence intervals for y. Well, how do you know what x values to substitute in to the software unless you know the range? So, you know, I'm kind of looking down my experience column. I'm modeling salary, remember, as a function of experience and gender. I'm looking down my experience column, and I see it ranges anywhere from 1 year to, it looks like my biggest one is, I think you might find it 25 years all the way at the bottom. So I know I better restrict my range to 1 to 25. Don't try to predict for a professor that has maybe 30 years of experience. That'd be outside the range of the sample data. The zeros and ones are easy, right? You know, make sure you put a 0 or 1 in there when you're predicting whatever your DV is. So that's what you would use printout number 1 for, okay? All right, printout number 2 is a scatter plot of your actual data, all right? And now, look, are you going to be surprised when you don't see lines, perfect lines or perfect curves here? No, you're not going to be surprised. In fact, you're going to expect non-perfection. You're not going to expect perfect lines or curves. If you see perfect lines or curves, that's a problem. You didn't do this printout right. Or you have perfect data, which is not correct either. Okay, deterministic data. All right, so you're going to see hopefully trends. Maybe you don't see any trends, but maybe it might help you see a trend. Like I'm kind of seeing possibly straight line trends and a difference between males and females. So that's a scatter plot of your actual data. Printout number 3, correlation matrix. What do we use this one for? Checking for multicollinearity. Now, be careful, because I had you do the correlation matrix for y, x1, and x2. But you don't care at this point. You ultimately care, but not for multicollinearity. You don't care about a high correlation, for example, in my case, a high correlation between salary and experience. It's pretty high, 0.88. But that's not a bad high. That's a good high. All right, that's a good high. A good correlation is a good one between a y and an x. The bad correlation, the one that leads to problems, is a correlation, a high correlation between an x and an x. That's multicollinearity. So I better look here at correlation between experience and gender. Oh, I'm in great shape. Hardly any correlation at all, 0 correlation. So see, you're looking for that. That's what you're looking for in this printout to help you address this multicollinearity phenomenon. All right, printout number 4. This is a printout of model number 1. Now, this may or may not be your best model, and later on you're going to give me a printout of your best model, so you're not really evaluating anything here. But at this point, if I'm you, I'm just making sure I can fit the first model. Can all these terms actually be estimated? This is where you might be missing a term, and if you are, that's a problem with maybe the way you created your data, like I showed you a little bit earlier under project notes. So make sure your x1 and x1 squared's in there. Make sure x2's in there, your interaction terms. Make sure that's all in there. Now, some of you at this point are going to see a non-significant model, a model that's not useful. Don't freak out, don't panic. Keep going. It's okay. You'll tell me about it. That's printout 4. All right, printout 5, this is your first test in your model building stage. This is the one where you test for curvature, and you do it by comparing model number 1 to model number 2. By the way, you can put labels on your printouts that match mine, but no more. Okay, so you could type here, compare model number 1 to model number 2. You can put labels like that, but you can't put anything else in there. We'll be checking for that, okay? Some students try to sneak stuff in there. I'm not sure why, but they try to. But just use the labels I'm using, no more, okay? Anyway, so this is a test for curvature. How do I know that? Look at the unforced row. Should be the 2 curvature terms. And the top row should be the terms in model number 2. We've gone over that a lot, okay? And then which p-value to look for? The last one. So there's a null hypothesis you're testing. There's an alternative. I'll go over that when we do the exam, okay? But this is actually telling me that I don't need curvature, so I'm going to drop curvature from the model. Maybe you need it. Maybe you need to keep it in there. All right, if you have to drop it from the model like I do, then your next printout is print number 6. That's the one to compare model number 2 to model number 4. Okay? And that's just going to be a t-test on interaction on model number 2. So this is where you just give me a printout for model number 2. And so I'm looking for the interaction term. There it is. And there's my p-value, and that tells me whether or not I have interaction. So some of you are going to keep it. Some of you are going to throw it out. Now, for those of you in the previous test who tested for curvature and needed it, your printout 6 is going to look different than this. So I'm going to put it up in the overhead, okay? Your printout 6 looks different. It looks like this. You're comparing model number 1 to model number 3. It's a partial f-test. Look at the top part of the printout. The terms in the unforced row should be your 2 interaction terms. I highlighted them there. Of course, you're not doing any highlighting, right? This is just to help you for this review. And the terms above it are the terms in the model number 3. And then the p-value at the bottom is the one you want. So your printout looks a little bit different if you keep curvature terms in there. If you throw it out, it looks like the one that I showed you in the on the Word document. Printout 6. All right, so printout 6, whichever way it looks, tells you whether you have interaction. At the end of looking at the results on printout 5 and looking at the results on printout 6, you know your best model. My best model is model number 2. Yours could be different. So your printout 7 is going to look something like this. Not exactly if it's not model number 2, but it's going to be either 1, 2, 3, or 4. But get your printout for your best model. This is where you start evaluating. Now you start evaluating numbers on this printout. Global f-test, p-value, adjusted r-squared, standard deviation. You start evaluating your model. Printout 8, confidence intervals, prediction intervals. You've got to pick values of the x's that make sense. That's why we looked at the first printout. You also have to put in values that make sense for the model you have, all right? If you don't have curvature in there, you're not squaring anything. I have an interaction term, so I had to multiply 2 x's together to get these numbers. So make sure you do these numbers down here correctly to get your correct confidence intervals, prediction intervals. And then the rest of it is the residual analysis stuff. Actually, yeah. So printout number 9 is a list of your standardized residuals. Remember, you're looking for y outliers here, so any number, absolute value greater than 3. I think I have one y outlier. Looks like around observation number 38, I think is a y outlier. I have a couple suspect. Printout number 10 is scatter plotted residuals versus your quantitative x. Remember, this is the one that checks for the curvature. I shouldn't see any kind of a curve here because I tested for it correctly. Or even an x outlier, and there's no x outliers here. Printout number 11, residuals versus predicted y. Now I'm checking for a funnel cone shape. Maybe slight, but it doesn't look too bad. This is a judgment call on your part. Maybe you have a strong trend and you tell me about it. Printout number 12, let me skip that for a second. Printout number 13, stem and leaf plot of the residuals. This is when you look for normality or something close to normality. Okay? Extreme skewness is going to violate the assumption of normality, but little skewness or even moderate skewness won't because of the robustness property. And then going back to printout number 12, graph of your best models. This should show a picture of your best model. It should have perfect straight lines or perfect curves. And it should match your best model. Remember, my best model is model number 2. Model number 2 does not have any curvature in it, so I shouldn't see any curves. That's why I see straight lines. Model number 2 has interaction. That's why I'm seeing lines that intersect, that are non-parallel. This should match your best model. If it doesn't, you messed up on getting your best model, or you messed up on getting this graph. One of the two. We have to figure out what it is. Okay? But that's what this should be. Okay. Well, when I come back next time, like I said, I'll do a formal review for the test. It'd be great if you already had your printouts with you and you could go along right along with me in answering the questions that I give you on the sample test. Anyway, we'll do that review next time, so I'll see you all then.